So to continue our square root practice, let's turn to our textbook on page 31. This is number 154, square root of 64.
Because we know that 8 times 8 is equal to 64. That's the first method. That's the fastest way in my opinion. But again, if we want to use this other method, since we're doing things by hand, the optional method / the tree method would get us that same answer. So I'll say, or you could have done it this way. We look at the 64, we look at the number under the bar, and we say, okay, prime factors. I see a 2 in there. That's a prime number. 2 times what gives me 64? 2 times 32. Is this number prime? No. So keep breaking it down. 32. Can we pull out a prime number? Sure. Another 2. 2 times what gives me 32? 16. So then we say, okay, well, is the 16 fully broken down? No. And notice I keep putting the prime number I'm pulling out on the left. This is the way I keep my work organized. I always put the prime number on the left, and the number that may be broken down more, I write it on the right. So notice 2 times 32, that's the original. 2 times 16, that goes back to the 32. So every time I break it down, I'm trying to keep it pretty organized. For the 16, pull out a 2. 2 times 8. Then we have for 8, we pull out a 2. 2 times 4. And for the 4, we're going to get 2 times 2. And once again, the idea is collect your pairs. Because you are looking for square root, we're going to collect the pairs of numbers that we have. And again, the reason it's pairs is because we're thinking square root. We're thinking groups of 2. So here's one group of 2. There's another group of 2. And there's another. So in other words, we've collected one of each of these. We're going to keep a 2 times a 2 times a 2. So the answer in this one is 8. Now notice the difference. In the last one, whoops, that wasn't the right page. In the last one, when you broke it down, you only had one pair. So you just kept the 5 from that one pair, from the 2 5s you had. In this one, when you had multiple pairs, you collected what was being repeated, and you multiplied it together. You multiplied it to get your 8. Once again, you have 2 ways. If you can just see that the number times itself equals the one under the bar, go for that. If not, use the tree method and go back and collect your things. Collect your prime numbers to see what you get. (156). The square root of 144. Well, once again, I know that that's the same thing as 12 times 12. That's what 144 is equal to. So I know this is the same thing as the square root of 12 times 12. Again, the first lecture, remember, I can rewrite it like that. I haven't emphasized that yet in this supplemental lecture. But remember when I taught this that we do know we can write a number as itself, just represented by multiplication under that bar. And in fact, if we had wanted to, we can even split the bar among the 2 numbers. And we'll get to problems where we see that happening in just a moment. But for this one, we see a 12 times 12. So we know that the square root of 144 is equal to 12. You did not have to show me this, but that's what you were hopefully thinking in your mind if you use the faster method, this method, where you just go straight and say it. The other method, I'll say or, would have been to take that 144, since you don't have a calculator, and to break it up so that you could see what it was made of. I would put in a 2. Let's see, 144 divided by 2, I'm getting a 72. So 2 times 72 is still equivalent to 144. Another prime, let's plot another 2. I'll get a 36. Another 2 will give me an 18. Again, I still have a prime number of 2 in there, so 2 times 9 and 3 times 3. So I've broken 144 up into all of its primes. I did the prime factorization. And I'm not spending a lot of time. I'm going to keep working problems with this table method or this tree method. You may have learned a table method. But with the prime factorization, that is something you've hopefully seen before in your past. It was a 060 or an essential mathematic topic. So that's why I'm not spending a lot of time. If you need more time with those trees, let me know, and I can go into more detail with that. But again, we've broken 144 up into its primes. Remember, the primes are the ones that are on the ends. You don't look at the 72 anymore because it was further broken. Same thing for the 36. You're only looking at these leaves here. That's what we call them. We call them the leaves of our tree. And when you're looking at them, remember, since you're looking at square root, you're going to look for pairs. Look for sets of 2. So let's see, we have one pair here, so we keep a 2. We have one pair here, so we keep another 2. And we have a pair here, so from those we get 3. And attach it by multiplication. Just like up here when you said 12 times 12, I can represent my number as multiplication. So 2 times 2 is 4, times 3 is equal to 12. And again, technically you could have written this as square root of 144 is equal to the square root of 2 times 2 times 2 times 2 times 3 times 3. And every time you saw a pair, you pulled out that repeating data. And you got a 12. Now let's start looking at some that aren't perfect, some that may have been a little more difficult if you had just tried to look at it like this up here. And again, I'm going to work it both ways because it's still possible to use both lines of logic. So number 158. We're asked to find the square root of 50. And remember, this right here, in the directions in this set we're in, this homework set, has asked us to just simplify. So it's not saying give me an irrational number. It's not saying give me a decimal number or any other such thing. It's saying break this down as cleanly as you can without you know, using any decimals or doing anything like that. And really, honestly, by hand, you can't get those square roots. So we are doing the best that we can with the calculator. Unless it's a perfect square, we just break it down as far as we can. So with this 50, we have two options. The first easiest option is to say, you know what? I remember that I can break any number under this radical up by multiplication. In other words, I know that I can say 50 is equal to 25 times 2. Now, when I broke this up with multiplication, I was being pretty smart about it. 50 can be broken into lots of things. But I'm going to choose 25 and 2 because 25 is a perfect square. So I'm being kind of strategic here and saying there's a perfect square number, which is 25 times a 2. That are the same thing. They're equivalent to my original 50. I'm allowed to break square roots up like that over that multiplication symbol. And once I've done that, the square root of 25 is 5, and I have square root of 2 left. So I get 5 square root of 2 as my answer. Now let's use the other method. For those of you who have trouble, some people I believe who are requesting this are having trouble identifying that perfect square when they're breaking it up. So the tree method is a really good backup method to have or to understand. So, or for the square root of 50, I could have said, okay, I have a 50. I'm going to break it up into its prime number. So first I'll pull out a 2. 2 times 25. Well, 25 is not prime, so let's break it up again. Let's see, 25, I'll pull out a 5. That's a prime number. 5 times 5 gives me 25. Look, I have all primes. And now I'm going to collect pairs. So there's 2, and then there's a 2 left over. So 50, the square root of 50, is equal to the square root of 2 times 5 times 5. I'll look at pairs, so my 2 5s come out to give me a 5. And I still have square root of 2 left up under the bar. You can either think of it as being left up under the bar, or you can just notice that here it wasn't collected, so it doesn't get to come out from under that radical. Either way, 5 is what you had, and it's still times the stuff left up under your bar, the square root of 2. Let's look at 160. The square root of 12. Well, that's not a perfect square, but there's two different ways I can approach it. The first way, again, is to say, can I pull out a perfect square through multiplication? Can I rewrite this as two numbers multiplied where one number is a perfect square? Sure. In 12, I have a 4. That's a perfect square times a 3. And I can rewrite that as square root of 4 times square root of 3. Remember, the square root of 4, that's a 2. So I'm getting 2 square root of 3. So if you're comfortable thinking of perfect squares and just breaking it up, this right here is your fastest method. This works for you. But if you'd like to see the tree method or use the tree method, let's work through that. I would take 12 and break it up. 12, let's see, I have 2, that's a prime number. Remember, you can pull out whatever prime you want. The idea is you eventually get it into all of its smallest pieces because you keep breaking it down until you can't stop. So you could have pulled out a 3 here. I chose 2 because I usually start with 2. So 2 times what gives me 12? A 6. I'll pull out another 2. 2 times what gives me 6? 3. Can I break a 3 down anymore? No. These are my prime numbers. These are my leaves that I would collect from my prime factorization tree. So now I look for pairs of 2. Notice there, I have a pair. So I'm getting a 2 that came out from under the bar, and that 3 is going to be up under the bar, square root of 3. If you wanted to see it maybe written a little bit better, what you just did in this tree was you said, okay, I can break that 12 down into 2 times 2 times 3. You found your pair of 2's, you pulled them out front, and you left your 3 up under. This method here is especially good for really big numbers. So I know the request was actually to work out some really hard ones. I just wanted to start with the basic stuff first, though. So we will get to some bigger ones where you may start to prefer this tree method a little bit more. Let's look at 162, though. We'll go kind of in order for a while. We're not going to do all of these, but we'll do most of them. 162, we have negative 3 square root of 48. When there's a number written on the outside of your radical, all that actually means is negative 3 times the square root of 48. So the idea hasn't changed any. It's just, remember, multiplication, you don't have to show that symbol between the stuff. So you have a times connecting it, a multiplication symbol. We do want to break this 48 down as much as we can, though. So we have two ways of doing it. We can say, do we have any perfect square stuff in there? Or we can use the tree. Let's practice using the tree right off, because actually for some reason right now I'm not thinking of a perfect square, which I'm sure there is one. I guess it would probably be a 9. No, okay, let's see. So we'll use the tree method first this time. So we have 48. We don't have to worry about that negative 3, it's just attached by multiply. So we are just focusing on the square root, on simplifying that. Then we'll come back and collect that negative 3. So the 48, we'll say 2. 2 times 24 gives me 48. Another 2 times 12, a 2 times 6, and a 2 times 3. So the square root of 28 is equal to the square root of 2 times 2 times 2 times 2 times 3. So I have a 2 times a 2 and a 3 left up under there. So what we get in our original problem is that negative 3 is still on there, but we replace the 48 with times 4 square root of 3. That's going in place of the 48. But of course, now we have 3 pieces attached by multiply, negative 3 times 4 and 4 times square root of 3. So negative 3 times 4, that's actually, let's see, negative 12 square root of 3. So the answer to this one is negative 12 square root of 3. Because again, a recap of what you did, you broke that radical down as much as you could. That's what we were doing here. We used the prime factorization tree. We looked for pairs. So we have a 2 times a 2 times a square root of 3 left up under. I wrote it here for you so you could see officially what was happening. Looking for pairs of 2 again, you get a 2, another 2, and the 3 is left up under. Since you had the 2 times 2 pulled out, that's a 4 times square root of 3. When you replace the square root of 48 up top, 3 times 4 is a 12 with a negative in front, and you still have that square root of 3. You can't go any further.